what they eat and what they poop out in the end is kind of rocks and minerals.
You're listening to The Cosmic Cast.
Hello and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. I am Marissa Lowe and I'm joined by my co-host Bea Baharier.
Hello.
And our special guest today is Bea Baharier from the Open University.
Hi.
Hello Bea, how are you doing? Thanks for joining us.
Thank you for having me here. I'm doing good. How are you?
Yeah, pretty good.
Well.
Yeah. So Bea, you are an astrobiologist, which is a very cool title. But before we plunge into your research, what got you interested in science and geology in the first place?
It's a long story, but to make it short, I guess I traveled a lot when I was younger, and I kind of saw all the impact that's happening by deforestation, because I spent a lot of time in the Amazons. And one day I hitchhiked, and a geologist from NASA gave me a ride.
No way.
Yeah. And I was talking to him about how horrible it is, like this whole deforestation and what's happening here and all that. And, he started talking and he got me really excited about, the idea that actually deep time can really teach us something about how to really save the environment, not just saying, oh, this is horrible and being an activist, because even activist is important, but actually understanding deep time to kind of understand the future is very important. And then also I got involved a lot with indigenous people in the Amazons, and a lot of their teachings of the elder kind of chiefs of the tribes really taught their kids to go ahead and get an education, because he said kind of in a way that the white person initially came here with guns and we had bows and arrows, so we didn't know how to fight them back in a way, in the same kind of warfare. And they said the warfare that we're going to fight now is knowledge. So if we're going to go and get education, if it's like a degree in science, a degree in medicine, a degree in law, we can fight back with the same knowledge. So kind of that whole experience made me feel like I have to get knowledge because this is important for me. And that kind of idea of deep time that actually really makes an effect about like how the planet works, and it's not just the current time if you want to make a real substantial change. And then I think as I learned more and more about geology, I constantly wanted to know about the bigger picture. So kind of what is life, because we know there was many extinctions in the past. We're not the first extinction, and there's many extinctions, and the planet is constantly changing and it's constantly adapting. And I think constantly the idea of the bigger picture, what is life really, and when is life and kind of a really effect on the planet and not effect on the planet, and what is it, got me in always constantly of this question of the bigger question of like life. So that's how I got into astrobiology.
Yeah, that's amazing. I mean, that's an amazing perspective to have, definitely. Although I do have to ask, how did you end up traveling around the Amazon and then coming across a NASA geologist?
Well, that was a mistake. I was just hitchhiking and he stopped. I don't even remember his name, unfortunately. But yeah, so I grew up in Israel. And in Israel, after you finish your high school, you go into the army. And then after you go into the army, like the first thing everybody does here is goes traveling, because you feel so stressed of like 2 to 3 years of just kind of a lot of like very harsh, difficult times. And then you just kind of want to go and explore. So I basically took a backpack with a tent and I guess some clothes, and I went hitchhiking in Latin America for a while, some time. And yeah, so the Amazons were amazing and beautiful, and I was enchanted by the fact of seeing indigenous people and how I guess people live in a way that's very, very different than what we know.
Yeah, and I guess being in such an environment like that definitely makes you appreciate the geology and the ecology of a place.
Right. There's not that many rocks in the Amazons. but it does make you appreciate the fact that it's an amazing planet. It's really an amazing planet, and the fact that it's also very sensitive to what we do. So that's the main thing that I saw, and that we kind of can live with it. We don't have to destroy it. So kind of that was what my main kind of feeling from that whole travel, of just trying to be less impactful on the planet and just kind of living with it, because that's kind of, I was just with a tent, so it's not like hotels and stuff like that. It was
so we can definitely tell that you're incredibly passionate about the Earth and geology in general. So I believe you did your undergrad in geology then.
right.
What was your path from that to starting the PhD?
My undergrad was in the University of Leicester, and it's very focused on I guess the Anthropocene and fossils and a lot of like looking at, I guess, kind of extinctions and ways of different things fossilizing. And so for my I guess my dissertation, I don't know if it's in geology, I don't think it's called a dissertation. You kind of need to do a mapping project for 6 weeks. I did it's in Spain, and I looked at the KT boundary, so kind of looked at the extinction there, and you could really see where we were. There was like hundreds of dinosaur footprints, which was really awesome. Yeah. And again, the whole interaction again between the life and the environment, and how we could see that, you know, in order for us humans to evolve, we needed to have the dinosaurs die out, unfortunately. But that in a way allowed mammals to continue evolving. So I guess from that, I really wanted to continue in pursuing really more education in that. I stopped for a while. I worked at like geotechnical drilling, and that was really boring. It's basically logging cores all day long and saying, this is sandstone with a bit of clay, and this is clay sandstone. And that was really boring. And I like felt like I really, this is not what I wanted to do. So I went back and I really wanted to do astrobiology. Like I knew that that's what I wanted to do, because I really wanted to kind of understand the link between life and the planet, like on a much larger scale. So I basically looked for researchers that are doing that. And I came across Claire Cousins. She is a lecturer and researcher at St. Andrews. And I went to do my master's there after I emailed her and said, if I will do my master's there, would she be willing to supervise me? And there I did a master's in geochemistry, and I specialized in astrobiology with her. And I got some samples from Iceland there. Fortunately, I didn't get to go to Iceland. But you know, Mark Foxpal, I think he was here a couple of weeks ago. Yeah. So he got the samples for me. And there I looked at a little stream from it's Kalingjafjall volcano, and it's basically a stream that has like really hot fluids, and then you go down to like really cold fluids, but in a distance of like, let's say, I don't know what, 30 centimeters, 40 centimeters, and you could see the extreme change of temperature, and you could see just like visually from the images that I saw, and that's why they collected the samples from there, that the color really changes from like this gray to this yellowy. So they collected it because they thought that the biology is being affected there. So what I did is from those samples, I looked at the mineralogy of them, the chemistry of them, and the biology. So the biology, I did DNA sequencing to look at the microbial community that they were there. Also look at the genes, mostly sulfur genes. So the possibility that any of these microbes can use sulfur as a metabolism, basically, together with the mineralogy. and that's the first time I ever did biology. So I'm not a biologist. This was all really exciting for me and different because I do rocks, right? And suddenly I'm looking at DNA, which is very confusing, and thinking about genetics and all this stuff was very new for me. And kind of looking how the microbial community correlates with the mineralogy and how the mineralogy changes along the stream.
Okay.
And basically to see how they change and what they use and how they use differently while they are all in the same bedrock. So basically in kind of the kind of conclusions that I came up with, I'm just kind of trying to summarize my master in like a few minutes, that the bedrock that was there was not the thing that was affecting the microbial community, because you had different microbial community within, I don't know, 30 centimeters away from one another, and you had different mineralogy as well in the fluid. So it's kind of more what affected the microbial community was the temperature, temperature range in this fluid. So that's when you're now trying to take that into Mars, because my analog research was eventually for astrobiology. So the idea was to use that as an analog site. So the bedrock was, and tell me if I'm saying too much or too little. I'm just trying.
No.
Okay. So the bedrock that it was on was more evolved rock. So usually what we see on Mars is more basic rock. We see more basalts. However, Iceland is also mainly basalts. So why would I use a Mars analog site for more evolved rock? So the idea was basically to look, does this have an effect? Really, does the bedrock have an effect? Can we go to Mars and say, hey, there's basalts here, this will have an effect on the microbial community versus more evolved rock? And also I was using it as an analog for Nili Patera caldera on Mars, which it's one of the only places that may have slightly more evolved rock on Mars. And again, it could be only a bias of detection because it's slightly cleaner from dust, basically. So so it could be that it's just detection bias and there's more evolved rock on Mars. But that specifically place, you also have sorry, it's master stuff. I feel like it's a long time ago. Hydrated silica. Yes. So there's more possibility that also it had evolved rock and also a hydrothermal environment. Area. So kind of using that as my analog site and saying, okay, if now NASA, ESA, whoever wants to go and look for signs of life, is there a bias of the bedrock? So kind of the conclusion is that the bedrock shouldn't be a bias of, okay, evolved or non-evolved rock or something like that, because there was still microbial community in both environments, and the main thing that changes is the temperature. It would be actually more interesting to look maybe where there's any evidence for hydrothermal environments, because that maybe tell us something rather than the actual rock.
That's, I mean, apart from being really beautiful sites, usually analog environments are obviously really useful for understanding, you know, Mars and the moon and places like that. I mean, at the time of recording, it was yesterday that the Perseverance rover successfully landed on Mars. I think it's worth pointing out that a lot of the work that goes into planning these missions and understanding the landing sites is based on analog research done on Earth. So that's really, really interesting.
So you want to hear about my PhD now?
So what took you from your master's into your PhD then?
So what, sorry, say that again?
What took you from your master's into your PhD?
I knew that I wanted to continue. I knew that I wanted to continue researching the interaction between life and the environment. I had a little taster of biology, and I thought it's fascinating how biology can really interact with the rocks and how you could do this kind of holistic research. It doesn't have to be just one aspect.
Yeah.
You can take in a rock and then take in, you know, a planet, and then take some genes, and it's from the smallest little thing to the biggest thing, and make a story out of it, you know. And it's amazing. I think the idea that you could look at something so small as one little gene and one little microbe, and then you could look at a planet, and then you could look at a rock, and you could make a whole story about life, and it's amazing. So yeah, so I knew that St. Andrews is working a lot with the Open University. So I applied for a PhD there. It was they were calling for, it was already like the proposal was already ready, so it wasn't like I invented the research. So yeah, so there it's basically, it's part of a bigger NASA consortium, which I'm working with, to look at sulfates interacting with magmatic intrusions. So Mars is filled with sulfates, doesn't have like substantial amounts of carbonates like we have on our planet. There's a lot of carbonates all over our planet, limestone everywhere. And Mars, maybe there is some very like unique places where you find carbonates, but definitely not as you see on Earth. But what you do see everywhere is sulfates. So for example, in Jezero Crater now, we do have sediments that are full of sulfates, and we have a volcanic cap unit touching it. So as I said earlier, with hydrothermal environments, which are more interesting to think about microbial communities or different things like that. So the interaction between magmatics and the sediments will create a hydrothermal environment. And because we know that Mars is filled with sulfates, and kind of sulfur metabolism is one of the most ancient metabolisms we know from our planet. It's very, very interesting to research that specific interaction between the rocks and the sulfates, to see whether that type of environment could have at one point in history of Mars supported life as we know it.
So how do you go about tackling that question?
So specifically for my PhD, I'm looking at magmatic intrusions from the San Rafael Swell in Utah, USA. And we have their sediments, the kind of red mudstones, similar to what we see on Mars. And we have sulfate veins as similar, like we see on Mars. You can see here, this is Gale Crater. And kind of gypsum and hydrite, anything between gypsum and hydrite and basanite, they're calcium sulfates with different amount of hydration. So basically none to 2 molecules of H2O within the crystal structure. And the interaction between a dike intruded into these sediments in the San Rafael Swell would have potentially released also the sulfates, but also the fluids within the sulfates to create a hydrothermal environment. And
that's because of the heating.
Yes.
The
heat introduced into the environment, releasing out the fluids and potential sulfates within the sediments and the veins of the sulfate veins, and potentially creating a habitable environment. So a habitable environment doesn't necessarily means that it was habitable. It doesn't mean that it was habitated.
It doesn't mean there was necessarily life there. Exactly. But
so the same thing on Mars. It could be that it was a habitable environment on Mars. It doesn't mean that it had life there ever. But to give it kind of an idea of where to look in case there was, you have to understand what is the potential for a habitat.
Yeah, I guess so. Just for the listeners, that's one of the hardest things about studying for life on Mars is we don't know how life forms. Essentially, that's one of the biggest questions we don't know the answer to. So you could have all the ingredients you need for life, but there's still that step of us not knowing, okay, what happens to make life after that? So for instance, Perseverance rover in Jezero Crater or ExoMars, which will be in Oxyoplanum, they're going to places that look like they're most likely to have life on Mars, if there was anywhere. But again, we don't know whether there will have been just because all the ingredients are there.
Right, exactly. Yeah, but you have to start from something. And
Exactly.
also kind of the history of Earth and Mars kind of correspond to one another in a way that Mars may have been more habitable earlier on in its life. It may have had an ocean covering half the planet. It may have had hot springs, while Earth was still a big ball of magma. So the thought that maybe if life evolved on Mars, it may have happened earlier on. And around the same time, we start seeing potential biosignatures from early Earth. So like 3.8 billion years ago, Mars started losing a lot of its habitability traits. So that's kind of why you keep going back to early Mars rather than present Mars, and kind of all constantly looking at like early metabolisms on Earth to look at potential life on past Mars. So yeah, so I look at so basically when I managed to do my field work before the lockdown, before the pandemic. And what I did is basically I took samples like as a traverse from the most unaltered rock to the most altered rock, including the magmatic intrusion. And supposedly I was supposed to do a lot of geochemical analysis on all of them.
Yeah.
I'm doing them, but very slowly, to understand in each step what chemistry changed. From the chemistry itself, if we're just looking at minerals and the chemistry, we could start thinking about temperatures and environment and different things like that. But then what eventually I'm doing now at the moment, parallel to getting some of my data, is modeling it. So using thermodynamics, that's the word. Thermodynamics equations that I'm not dealing with because I have a software that does it for me. Looking at what type of fluids formed in this interaction between the dike and the sediments. So the idea is to reconstruct the fluids that formed during this interaction.
Yes, yeah. So what type of inputs do you need to know for that? Is temperature, for instance, and I assume the mass of rock that will be there, that will be interacting with the dike and things like that?
Yeah, so those stuff I don't need to know. Those stuff the software tells me. No.
Okay.
So basically what we do is I look at the mineral composition. So I'm using SEM, microprobe, Ramen, and XRD. So kind of to get the full view of everything as much as I can. And then to get the kind of bulk composition in oxides, and also to understand the crystals that are forming, because the crystals may have different may have the same chemistry, but the crystals that are forming are different crystals. And that's also relating to temperature and pressures, and water to rock ratio. Then when I kind of get that full picture, I can put into the software, put a different amount of oxides, and then interact it with a fluid. And then I have to, that's also a tricky question of thinking about what fluids to interact with. Because fluids just they're not pure H2O. And you have to think, what are the original fluids before this interaction that would have been released? So because my sediments are Jurassic and they were formed underneath the Sundance Sea, I took initial composition of the Sundance Sea, kind of looking at the difference between modern ocean and Jurassic Ocean, and kind of playing around with that to really see what fits the result. Because basically what I'm trying to get to the final rock result that I have in my hand.
Yes, yeah.
But by reconstructing the past. So then I slowly titrate in the rock that I have, the chemistry that I have into the fluids to see what are the interactions, what minerals am I forming? Okay, and that's from the unaltered rock into the fluids. So that's kind of going back in time in a way. And the idea is to play around with it to kind of, figure out what temperatures, what environment, what all that would give me the resulting altered rock.
Okay, so you're trying to basically work out, you've got your starting composition and you're working out what ingredients do I need to add to this in the model to sort of get the end result.
The altered one at the end,
Yeah, which I have the end in a way as
Yes,
well.
yeah.
So they had the traverse of the whole alteration
Yeah.
pathway.
Yeah.
But then that will give me that basically the temperature of the fluid. That would give me the composition that was inside the fluid. So what species, elemental species, were available for microbial life during X time, and then basically the final idea is when I get this fluid to understand what species were in the fluid, and what were the temperatures and all that, is basically to go into the lab, recreate those fluids in a lab, and really putting them under Mars conditions and really checking can they support life, and what type of life, and what are they missing, and really make this kind of parallel to Mars, because the models will tell me maybe something about Jurassic fluids, not necessarily Mars.
Yeah.
So the idea is also tweaking it towards Mars, also the fluids, and seeing the differences between them, and also tweaking it to Martian environments eventually.
So when you're, as you said, these the fluid interacting with the rock can produce certain minerals. What minerals in particular are you interested in? Is it these sort of sulfates, or are there any other ones as well?
No, not specifically, because we have sulfates there. They're there. So I'm going to checking a lot of sulfates. I'm going to get sulfates. I'm not looking for specific stuff. At the moment, I'm trying to reconstruct what existed.
Okay.
So it's not, I'm not looking. So we already found the analog site. Now I'm trying to understand what's forming in this interaction.
Okay.
Because in the end of the day, can this analog site tell me something about Mars? That's what's interesting, not what minerals would this form.
Yeah.
Eventually, when I will get the fluids, then it will be interesting to see what is in the fluids and what is missing, if it can or can't support life, basically.
Yeah. So you say you're going to take that step to applying it to Martian conditions. I guess first of all, what is applying Martian conditions? And then how do you decide whether under Martian conditions it can support life or not? Because supporting life is such a wide range of things. Like on Earth, there's extremophiles that can live in places that nothing else can live and stuff like that.
Right. So first of all, the basic stuff is the first step is chemistry.
Yeah.
So I'm now just looking at Earth stuff. Looking in the interaction is just Earth, because I want to make it very so to use the analog site as its best, and trying to get the perfect site for perfect result for the analog site. Then eventually I am going to look at Martian data, right? I can't just say, okay, this analog site is cool and all that. I need to look at Martian data. First of all, change the chemistry. If I'm looking at, I don't know, there's 10% of, I don't know, iron oxide, I said that, and in Mars you actually only have different amount. I'll have to tweak that first of all, and see really what's the difference between my analog site on the chemistry side and the difference between Mars. Then of course, when you're looking at life and environmental life, so of course, for example, current Mars, present Mars, you wouldn't assume to have liquid water on the surface with microbes in, because you know, anything that's there, first, it's not liquid water, and radiation would kill anything that we know. So if I'm looking at current Mars conditions, I know that they wouldn't be in a fluid and they wouldn't be on the surface. So I'm not in that part of my PhD just yet, but let's say, for example, if I want to think about current life, you would have to think about beneath the surface, or within crystals, or within sediments. So this is subsurface stuff. So even if these fluids may have formed on Mars at some point in the past, I will need to maybe evaporate them to see the results afterwards, and see maybe what the crystals formed later on, to see if the kind of evaporate could tell me something about maybe habitat potentially. Again, I'm not in that part of my PhD yet, so I can't tell you one-to-one, but again, if we're looking at past life, then we could start talking about surface water. Then you could start think about how much oxygen did I have in the environment? What kind of atmosphere did I have? And again, all of these are not agreed upon entirely. So even on Earth, we have, oh, maybe we had oxygen then, or maybe we didn't, maybe we had this amount, maybe. So even on Earth, we don't know exactly what was the atmosphere like in the past. and there's a lot of people believing different things, but also on Mars. So when we're looking at a habitat, we have to think not only about the space, not only about the food that it needs, but also about the point in time that it may have had that place.
Yeah. It's really difficult for Mars. Because even when we talk about habitable time, like at a period in which Mars might have been habitable, we're talking about hundreds of millions of years that we narrow it down to. We essentially say the Noachian period, which spans what, like 3.8 billion years to 3.65, something like that. So 150 million years.
Yeah, we say also into the Hesperian.
Yeah, into the Hesperian
environments, and then you see that's again into the time zone. You're thinking, great. A lot of people say if anything evolved on Mars, if life ever evolved on Mars, and to survive the late heavy bombardment, it had to be, you know, in extreme environments of high temperatures, because if it had a lot of bombardment, so then you have to think about that back. So if it's life, maybe during the Noachian you would have an ocean, maybe. That kind of life could survive in an ocean, and then other life would need to survive in hydrothermal environments. So it's constantly tweaking it relative to time and space, basically.
Probably quite a common question we ask any astrobiologist is, when we're talking about life here, what does this life look like to you? What's it doing?
What does it mean by what do you mean?
What are we picturing here? You know, I feel a lot of people listening might think, oh, life, trees, humans, animals, things like that. But we're obviously talking about something very different on a very different scale. So what sort of processes are going on here? What does this life look like?
So on Mars, particularly, probably microbial life. There isn't anything else that says anything else. And again, as a scientist, I can only look at what I can test in a way. So we can only look at life as we know it. There's maybe life as we don't know it, but I don't know it. So we're looking at what we can, and what we can is looking at water-rock interactions, basically microbial life that can, in a way, use rocks for their nutrients. So kind of, you know, what they eat and what they poop out in the end is kind of rocks and minerals, that kind of life.
Just like us geologists.
Just like us, really, right, exactly. Sitting around eating rocks all day long.
Well, I know lab work is a bit tricky at the moment, but how are things looking for the next few months or for the rest of your PhD project?
So I'm in my modeling stage. So that's good in a way. I can't stand being in front of a computer anymore, but it's it's good that I could start doing some modeling. Hopefully the idea is also to get some ramen. I didn't manage to do any ramen yet. But really,
so just for the listeners who don't know what ramen is.
So ramen is later they can say the vibration between the molecule, between the atoms, creating the molecule that creates the crystal, to understand what mineral it is. So for example, I so far used an SEM, which an SEM basically looks at the chemistry. So SEM basically shoots a bunch of electrons at my rock, and it kind of excites the electrons within the rock, and they pop out electrons back. And as they pop out, they release a kind of a characteristic kind of photon, and from that you could tell the chemistry of your rock. However, that's not enough to tell you the mineralogy, because different minerals can have the same chemistry. So Raman, looking at that vibration between the atoms, can tell you about the mineralogy. Now, Raman is specifically interesting and important for me because we also have Raman on Perseverance.
And ExoMars will also have it. That's
yes.
Give it a shout out as well.
We're not sponsored by either.
Well, I kind of am.
No, just because I think because it just landed yesterday, and you know, it's kind of exciting. So I'm thinking about, I want to get my ramen result before they get their result.
Yeah.
Because I just really want to compare, because the minute you have compare 1-to-1 data, and it's like, wow, like I could put the puzzle together from Mars. That's like the most, I guess, exciting point for me, that I could actually say my data looks like that or doesn't look like that, because that says something, even if it does or doesn't. But the fact that I can compare it and say something about it, that could be amazing. Yeah, so that's the future, doing some ramen, modeling. And yeah, hopefully when all this will be over, I can go into the lab and make some fluids.
So aside from all your astrobiology work, I believe you've been involved with a really cool project called Dance Your PhD, which I saw it on Twitter the other day. We'll put the link in the episode description. Yeah, can you tell us a bit about that?
Okay, so I really got into kind of science communication lately, because we're all online all the time. And I think we're all getting a bit fatigued from looking at PowerPoints and people talking, and kind of also the idea that science and scientists are seen as very boring people sitting around with diagrams talking about numbers all day. And I don't think that's true. And I think, especially as planetary scientists, we're all doing it kind of out of passion. We're not doing it out of like, feeling of we need to, I don't know, do something because there's a problem in Earth now that we have to solve. And I don't know, it's kind of very much very creative ideas, very creative thoughts, and it's very much out of passion. So when I saw there was this Dancer PhD competition, I was like, yeah, I want to put my passion into art, because it is what we feel. We're not just numbers and graphs and diagrams. It's a very passionate science. Anything to do with space, it's like wow. Like, so I wanted to convey it as a dance, but without dumbing down the science. That was very important for me. So yeah, so I thought about how do I talk about geology in a very exciting way. And I thought, okay, everybody likes David Attenborough, but we have to do it as a dance. So I thought about a classic narration, and in the background, you have the animals kind of fighting and having fun or doing whatever they're doing while there's like a narration over it. And instead of the animals, you would have dancers doing the geology in the back. So yeah, so the idea was to basically have it going back in time, and the dancers become the geology. So the whole idea was, okay, so we have the water, and kind of in the beginning you have the water, that it's kind of the beating heart of life, right? Because we have to have water for life. And that's kind of what astrobiologists do a lot. They look at water. And the dancers there are wearing blue, and they kind of, as the narration moves, as the water moves, as the story moves, the clothes change, the environment changes, and it's constantly evolving. But yeah, so basically it was really important for me for people to see it rather than just being told it. Because I think geology is something that's really difficult to see, because we're talking about the past.
Yeah.
And nobody ever saw, a mountain being built. So yeah, I was trying to make them see it as a dance.
Yeah, no, I had a watch of it the other day, and it was really, really cool. Where did you film it? It looked like you were in some really nice settings for it.
Yeah, so mostly most of it was in the Dead Sea in Israel.
Wow, okay.
Yeah, that's why I'm floating. There's a scene there that I'm floating. Yeah. I'm floating on water. Yeah. Nobody said anything about that, but that was like a really difficult scene, because I was dancing while I was floating, and there was like I had a drone above me filming me. But yeah, so most of it was in the Dead Sea, and then some of it was in the Ramen crater. It's a big crater down south here. And they actually have a Mars analog site there called DMARS. So it's like the one you have in Utah. So it's part of the Mars Society. So I went down there, and there's a place called the Chocolate Quarry. And that's where the final scene where there's in the end you have like the Ramen and Sherlock dancing, because Sherlock is the arm, the habitability detector that Perseverance has.
Yeah.
So if you go to the end of the movie, you could see that you have somebody, one of the dancers dressed as Sherlock Holmes.
Okay.
Yeah, and she has like a little badge there of how do you call it? I don't remember the name of it, but the badge that they put on Perseverance. Do you know about that badge? For COVID, to kind of reach out to all the healthcare workers in the world.
That's cool.
Yeah, so it's like a snake
Yeah, so
around
there's
Earth,
stuff in the middle. Yeah,
right?
yeah,
But they have like something going out to Mars.
that's cool.
Oh, that's
Yeah.
nice.
So I made that patch and I put it on Sherlock, because
Right.
that's Perseverance's arm. And then it's dancing together with another dancer that she's an Indian dancer, because that's to represent the Raman.
Mm-hmm.
Oh, yeah.
And I don't know if you know, but Raman was invented by an Indian guy called Raman.
Mm-hmm.
Oh, okay.
Yeah, and I guess it was that part was important for me, really, to represent the fact that even though it's an American mission, but the science that is there and the people that are there are multicultural. And they're coming from different backgrounds. Even though I think he invented Raman maybe, I don't know, a century ago, don't know how long ago, but his science that came from a different culture is still represented on something great as getting to Mars.
Yeah.
Yeah, and that was filmed in Machtesh Ramon and Mitzpe Ramon, the final Mars scene.
Yeah. Well, it turned out absolutely amazing. I will put the link to it in the episode description, so people should definitely check it out. But yeah, wow, I feel this has been a very inspiring episode.
Yeah, I hope so.
But yeah, unless there's any other bits you want to chat about, we do have one final question that we ask all our guests.
Okay.
Otherwise, this probably is a good place to wrap it up.
Okay, great.
Well, thank you very much, Bea. We have one final question to ask you that we ask all of our guests, and that is, if you could be doing something else completely different, either in academia or outside of it, what would you want to do?
I don't know. Well, I guess that kind of the classic thing that I'm thinking about, but it's just kind of something that's always in the back of your head when you're doing astrobiology, is being an astronaut.
Yes.
It's basically just being the geologist in space.
Yeah.
Yeah.
So like, yeah, I would definitely want to be an astronaut.
Well, you know, ESA made calls for it, 31st of March.
I know, and I thought I was thinking about it, but I haven't finished my PhD yet.
Yeah, but if you could be an astronaut, PhD, you know.
But wouldn't it be nicer to be a PhD astronaut?
Exactly. Well, you could just finish writing your dissertation while you're in space.
Really fast, right? They're just like, guys, give me this half an hour here. I need to just write my last chapter.
Yeah, fine. Yeah. Or as you're taking off, just finish writing it. You know.
So boring, right? Having to wait to get to Mars 6 months. I could do my my dissertation at that time.
Yes.
Find a hobby. Writing your dissertation.
Exactly.
Well, thank you so much for joining us, Bea. This has been a really interesting discussion.
Thank you for having me.
For the rest of your PhD.
Thank you so much. You too, and guys, take care.
Yeah. So if any listeners out there are looking for any more Earth and planetary science content, all of the links to our Facebook, Twitter, and Instagram are in the episode description. And thanks everyone again for listening, and we will see you next week. Goodbye.
Bye.